Okay, good morning, everybody. Let's get started. We are going to finish Lecture 6 in a mere moment, which will complete our theme on the tools of the trade. We've touched on artificial neural networks, evolutionary algorithms, and we'll finish our discussion of physical simulation. All of these three components you'll be gradually integrating over the course of your 10 assignments. And we'll spend most of today starting in on our history component of the course. Again, evolutionary robotics is a young field. So in Lecture 7, we're going to travel all the way back to the early 1990s and look at the first two experiments in evolutionary robotics. Next time, we'll talk about a series of experiments that were done, again, in the mid-90s, when evolutionary robotics was just getting started. And the idea here was what came to be known as minimal cognition. What is the simplest possible robot you can create in the simplest possible task environment, simplest fitness function, simplest evolutionary algorithm, simplest neural network? How minimal can you be that when you start to evolve behaviors for that minimal agent or that minimal robot, somebody might point at that robot and say, maybe it's not intelligent yet, but it's on the road to becoming intelligent. It is starting to exhibit some of the building blocks of intelligence. What are some of the building blocks of intelligence we've talked about in this course so far?
Pushing against your environment.
Pushing against your environment, observing how the world pushes back. So the agents we're going to look here are minimal, but they're still embodied. They have the ability to interact with their environment. What are some of the other building blocks of intelligence we've touched on?
Pattern recognition.
Pattern recognition. They're going to have to sense their environment and recognize danger from opportunity. What else?
Passing the Turing test.
Passing the Turing test. We're not going to see any minimal agents that pass the Turing test yet, but maybe someday. Okay. Why would we want to create such minimal agents? Well, if we do, and they do start to exhibit the building blocks of intelligence, like the Bratenberg vehicles, maybe they're simple enough that we can open them up and try and understand what's going on inside. We'll see some of that in lectures 8, 9, and 10. We'll then switch and have a pair of lectures on locomotion. We'll talk about legged locomotion, which is particularly challenging for animals and robots alike. And then bipedal locomotion, which is even more difficult than that. And it took all of us a few years to get the hang of that in our early days. Locomotion is a big part of robotics. There's a fundamental link between locomotion and intelligence. And a good way to think about that link is to think about why plants don't have brains. They don't need to get from point A to point B. So a whole group of species on this planet have settled on a solution, which is I'm going to stay put, and whatever I can collect from my local environment is good enough for me. Then there is a whole other collection of species of which we are a part that says we will go to the food, the mate, the opportunity, and so on. Traveling about, however, in your environment is very difficult because the patterns you wish to detect move relative to you as you move. There are a number of other challenges that are raised by trying to get from point A to point B. So there's a fundamental link going all the way back to Shaky the robot that we saw in the 1970s that connects this link between locomotion or movement and intelligence. And we'll talk about that in lectures 11 and 12. Okay, so that's where we're heading. Today, for the undergraduates, you'll be starting in on assignment 4. In assignment 4, you're going to be adding the 5th and 6th component of a robotics experiment, which are neurons and synapses. You've already done objects, joints, sensors, motors. Now we need to make connections between sensors and motors, which are going to be neurons and synapses, which transform the incoming sensory information to the robot into motor commands, which cause the virtual robot to move in its environment, which changes its relationship with the environment, which changes its perception, which changes its sensor values, which again flows through the neural network, and around we go. At this point in your assignment, just before you tackle assignment 4, you have basically a Ragdoll robot. It has objects and joints that connect them together, but they sort of hang limply. The moment you connect up the sensors and motors, suddenly the joints will become rigid and the robot will start to move actively in its environment. Up till now, you have a passive robot which has no ability to push against the world. Now when we add in neurons and synapses, it will do so. Any questions about assignment 3, assignment 4? grad students, you're moving on to 7 and 8 if you haven't tackled those already. A question about logistics for assignment submission. A couple students were having some issues with Reddit. If for some reason you cannot copy and paste your Reddit links into Blackboard, if you post in your Imager or your YouTube links directly into your Blackboard submission, that's fine too. You can skip over Reddit if you need to. All good? Any other questions? Okay. So we'll finish off lecture 6. And as you'll recall, we were looking at this hierarchy that we've been building, which is down in the engine room, we have Open Dynamics Engine. And I gave you sort of a crash course in physical simulation last time. We touched on the various elements of a physical simulator. Again, they get more complicated, each of those components, as you go down more into the details. But for our purposes, we have ODE, which is operating at the lower level. And then we have on top of that the C++ side of PyroSim. And what PyroSim is doing is exploiting the physics in the physics simulator to simulate sensors, motors, neurons, and synapses for you. That's the mid-level. And then on the top level, you are writing Python code where you call the PyroSim library and you send objects, joints, sensors, motors, neurons, and synapses to PyroSim. It does its thing in interaction with ODE, and then it sends you back sensor data, and you use that sensor data in your evolutionary algorithm, which the undergraduates you haven't got to yet, but you will shortly. Okay, so we got those 3 levels. So we spent most of last time talking about these lower levels, and just at the end last time, we jumped up to the PyroSim level. ODE doesn't have any sensors inside of it, so we need to exploit the physics to simulate them. We looked at which aspects of the physics engine you might want to exploit to simulate touch sensors. We looked at which aspects of the physics engine you might want to exploit to simulate photoreceptors or light sensors. They're not perfect. They don't deal with occlusion. You could start to try and imagine a more sophisticated light sensor that is able to deal with objects between the sensor and the light source, or that can deal with shadows. There are ways you could do that. We're also then going to exploit some aspects of the physics engines to simulate motors. So how do motors work in this case? Well, motors are obviously things that we attach to the joints, and they're going to supply, ultimately what a motor does is supply torque or rotational force to the joint, and that joint will try and change the relative angle of the pair of objects connected by that joint. How does that work in ODE? We first of all create a motor by setting a parameter at the hinge, which is the amount of force, maximum force that the motor can ever supply. We then need some desired angle. So our neural network is going to, the output layer of our neural network, as you recall, in the motor neurons, they output a number, and that number is going to be treated by PyroSim as a desired angle. So whatever the incoming sensor values are, the values arriving at the motor layer, those are desired angles. And the motors in ODE are going to translate those desired angles into torques, which are applied to connected pairs of objects. So we have our desired angle. Then we have our actual angle. So we can query the joint and ask, what is the actual angle between connected pairs of objects? And we finished last time by touching on this non-intuitive aspect of PyroSim, which is when you connect pairs of objects together at that instant in time, the angle between that pair of objects is 0. If I connect these pair of objects like this, the default angle is 0. If I apply torque that extends my lower arm away from my upper arm, that's a positive angle. And if I flex my upper arm in towards my lower arm up towards my upper arm, that's a negative number. So we're going to use positive numbers for extension and negative numbers for flexion. Okay. Actual angle is 0. As the robot starts to move around in its environment, obviously the relative angles between pairs of connected objects are going to change, and they're going to drift away from 0. We take that actual angle, then compute the difference. What's the difference between the desired and actual angle? The greater that difference, the more velocity or the more force is going to be applied at this point. So it's a little strange here in ODE that we're using velocity here. We're setting the velocity to be the difference of this. For our purposes, you can just think of the fact that a joint is going to receive more torque if the desired angle is more different from the actual angle. Make sense? Okay, so let's look at a cartoon example here. Again, we have our biped that we're looking at from our quadruped that we're looking at from the side here, and the current angle at the moment between this upper leg and the main body, let's assume that that angle at the moment is 0, and the desired angle theta here is 60. The difference between 60 and 0 is 60. So we have an error or a difference of 60. We supply that to the motor, and the motor is going to apply a torque that is going to try and reduce that difference. That difference is large, so it's going to apply large force. At the next time instant, remember that a physics engine is updated we're updating our physics engine in discrete time steps. So at the next time step in this cartoon example, we'll assume that the torque and the other forces that are acting on that right upper leg have caused it to rotate a little bit closer to the desired extension of 60 degrees. So now the difference between them is 40. Let's assume that the leg has rotated forward 20 degrees. The desired angle is still 60. The error is 40. What can you tell me about the torque that's going to be applied at this time instant?
It's going to be slower.
It's going to be slower. It's going to be less torque, right? Less force is going to be applied. So at the next time step, actually I should update this cartoon. It's probably not 20 anymore. There's been less force that's applied, so the difference, the leg is going to move a little bit slower, and the distance is probably going to decrease by less than 20 degrees, as it did in the previous time step. So if you imagine now, if you simulate this mentally, you can imagine that this right upper leg is accelerating towards 60, but as it gets closer and closer to the desired angle of 60, the difference becomes smaller and smaller and smaller. So the torque, or the force that's applied by the motor, becomes less and less and less until it reaches 0. What happens when the torque reaches 0?
The leg keeps swinging.
It might keep swinging, right? Because we have some momentum. So the leg might swing beyond 60 degrees to 70 degrees. And now the difference is minus 10 in the other direction, which means now we're going to apply torque in the opposite direction to start to flex the leg back in. So again, if we were to simulate this all the way out, we might see the leg overshoot 60, come back, and gradually settle at 60 degrees. And assuming that our desired angle remains 60 degrees, the leg will be held by the motor at 60 degrees. Okay. But of course, if our robot is instrumented with a neural network, the desired angle is probably not going to stay 60 degrees, because there's a motor neuron somewhere in that neural network that's outputting 60. If the sensor values change, then that value of 60 is probably also going to change. So let's put everything together now and assume we have this very simple cartoon neural network that you see in the bottom left here. We have our quadruped that we're looking at from the right side. We'll ignore the left front and the left back leg. Assume we have a touch sensor in the right back leg, T1, and a touch sensor in the right front leg, T2. We'll assume we just have these two touch sensors, and we have one motor, M1, which is the motor that's connected to the joint, which connects together the right front leg to the main trunk of the robot. Two sensors, one motor, two synapses. And at this first instant of time, let's assume that both legs are touching the ground, which means both touch sensors are firing. So our input layer is 1. I haven't specified the synaptic weights here, but let's assume that whatever those synaptic weights are, the raw sum that's computed at the motor neuron is 60. Remember that we can then take that raw sum and squash it by an activation function back down to some desired range. Let's disregard the activation function for the moment. No activation function, just the raw input, the raw sum, which at this point is 60 degrees. So like we just talked about, the motor is now going to apply a torque that's pretty strong, because there's a pretty big difference between 0 and 60, and the right front leg is going to start moving. The moment the right front leg starts moving, the front touch sensor stops firing, because that foot is no longer in contact with the ground. which means there's a change at the input layer. Now the input values are 1, 0. We're not supplying a data set at the input layer of the neural network. The values at the input layer are being generated by the movement of the robot. This is the first time we've seen in detail closing of this loop through the neural network, through actions of the robot, out through a change in the interaction between the robot and its environment, back to a change in perception. Let's continue this example. Let's assume that when the input layer changes to 1, 0, depending on the synaptic weights, the output layer changes to minus 90 in this case. What's going to happen at the next time step? So the output neuron here, M1, is outputting a value of minus 90. And remember that we're interpreting that value as the desired angle for that joint. The neural network is saying, I want the joint to rotate to minus 90 degrees. What's going to happen in the physics engine at this point in time?
Is that going to apply torque to put the leg back down?
Exactly. So it's going to apply torque or rotational force now in the opposite direction because we have a negative number. It's going to apply torque towards flexion. It's going to try and rotate the leg in towards the underside of the robot. Flexion is always away from the body. Flexion is inward. So it's going to apply torque where the leg may or may not start to rotate inward. Why may it not start to rotate inward at this point in time? It just rotated outward, and now we're applying force in the other direction.
It might still be moving the other direction if there's momentum.
Exactly. So there's momentum. The leg has a mass associated with it, and it just moved. So there's momentum, which the physics engine will take care of for us.
This might be kind of a silly question, but
Yep.
Is there like leeway in between where it like catches if it's rotating, or not really in a virtual environment?
What do you mean by leeway?
Like with some gear systems, if the teeth are not tight,
Yep.
it will need to like rotate before they catch each other and can start like turning the other direction.
That's a good question. That's not simulated in the physics engine, but you can go in and make a more sophisticated motor. We're assuming that the moment torque is applied to a joint from a motor, it's going to apply force to the pairs of objects. How the acceleration of those objects changes depends on the other forces that are acting on the objects, like, for example, momentum. Yes?
So if you include more time steps in a simulation, is your chances of it overshooting the desired angle decrease because it's able to lower the acceleration of time?
That's a good question. Not if we add more time steps, but if we reduce dt or delta t, the amount of time between one time step and the next, which we talked about last time, makes it more accurate, which means you're probably going to get less overshoot. Right? Remember that as we make dt smaller, we generally get less change in motion between one time step and the next. So it's likely going to be a much more smoother transition towards the desired angle, which again you can play around with in your code. Okay, so let's assume there's some momentum, so it's not immediately going to start to flex the leg back inward. What's going to happen at the next time step? Maybe the leg slows down because there's torque pushing in the other direction. What can you tell me about the sensors at the next time step?
Hit the ground?
Maybe. We have the front leg which is accelerating forward, and we're assuming that it's still accelerating forward even though there's force pulling back. So it's not touching the ground yet, it's actually going in the other direction, unless it hits some other object in front of it.
So you're not simulating the tip of the robot yet. It could fall over.
It could fall over, right? So there's momentum elsewhere. Maybe the robot tips forward and now the front leg comes in contact with the ground. Maybe, but before that happens,
The sensor's values would change, and if it goes above a certain angle, it might not even see ground anymore.
do the sensors change value?
Well, if they don't change value, since the angle's increased, more torque will be applied.
Exactly. So let's assume for our purposes that our leg is front leg is rotating forward. We're now applying flexion force in the other direction to pull it back in. So it's slowing down in its forward acceleration because it's about to start going the other direction, but we're not there yet. So the front leg is by definition still off the ground. Let's assume that the back leg is still on the ground. which means the input layer, even though there's change in motion of the robot, the front leg is slowing its extension acceleration. Even though there's change in motion, there's no change in the input layer. It's still 1, 0. Back leg's on the ground, front leg is off the ground. So what can you tell me about the motor layer?
It's not going to change until it receives another input.
Exactly, it doesn't change. So we're still, at the next time step, outputting minus 90 desired angle to the motor, right? So assume that happens for a number of time steps. The arm slows down, and now it starts to accelerate inwards back towards the body. Still back leg on the ground, front leg off the ground. So input layer is still 1, 0, 1, 0, 1, 0, 1, 0. The leg is coming back down again. What's going to happen in the next few time steps?
It's going to hit the ground and change again.
It's going to hit the ground. So the front leg is eventually going to hit the ground, and when it does, we're back to this situation. Suddenly, the input layer changes from 1, 0 to 1, 1. Now what happens? How does the motion of the robot change now?
So if there's momentum, wouldn't it, I mean, in theory, it could keep rotating?
It could keep going, depending again on the orientation of the robot's body. It might sweep, it might strike the ground and then start to rotate up towards the belly, maybe. Who knows? Let's assume for the moment there's enough friction and it slows down that now we have 1, 1 again. So now the motor neuron is trying to rotate the front leg back up again. Let's assume that it starts to go back up again. We're back to 1, 0. The leg starts to slow down and flex back in again. Front leg comes in contact with the ground. 60, leg starts to rotate back out again. What happens as we continue on for dozens or hundreds of time steps now?
The robot does like an inchworm kind of thing.
The robot does an inchworm form of locomotion, right? So we now have an oscillation. The right leg is sweeping out, coming back in, and by doing that, maybe it's pulling the robot forward a little bit, and we get locomotion. The robot starts moving. In assignment 4 now, when you add sensors and neurons, you're going to see exactly that. With your scissor bot, which is not too different from the robot you see here, just these two pieces, you can actually get forward scissoring locomotion with something that is as simple as the Bratenberg vehicle. There's no sine function in here. There's no sine wave. There's no oscillatory pattern embedded in the neural network. That oscillatory pattern is arising from this embodied loop, right? Sensation, action, interaction with the environment, changed sensation, changed action, and around we go. Questions?
Is there a time sensor?
Is there a time sensor? There is not a time sensor in PyroSim. It's a good question. We should put one in. Okay, so I didn't mention what the synaptic weights here, so just as a refresher on your intuition about neural networks, what are the synaptic weights that would produce these two output patterns given these two input patterns? And how do you know? Yes?
Would it be negative 90 from T1 and then 0.70 from T2?
So this one is definitely going to be minus 90. It has to be, right? 1 times x has to equal minus 90. So x equals minus 90 here. So we have minus 90 over here. 1 times minus 90 plus 1 plus. That sounds about right. Is that right? Oh, no, sorry. Minus 90 plus 150. 1 times minus 90 is minus 90, plus 150 gives us 60. Make sense? Okay. Again, this is a cartoon example, but just to show that with all of these pieces in place, we can get interesting behavior, maybe not complex behavior, but interesting oscillatory behavior with a very, very simple neural network and a particular kind of body. if we change the length of the legs or the strength of the motors or the geometry of the trunk of the robot with exactly the same neural network, we might get a different pattern of locomotion. As we just saw, this oscillation depends on the mass distribution and the friction properties of the foot when it scrapes against the ground. If we want to change the robot's behavior, we could go in and change these two synaptic weights, or we could make changes to the body. That's the thing that distinguishes robotics from other approaches to AI. Most other approaches to AI were only focusing on making changes to the neural network. In evolutionary approaches, we can change the neural network or the body. Okay, that concludes our discussion about physics engines. Any other questions before we move on to history? Okay. Okay, so as I mentioned, evolutionary robotics is a relatively young field. Back in the early 1990s, there were two experiments. One came from an Italian researcher, Francesco Mondada, working in Switzerland. And the other experiment we're going to look at in a few minutes came from some English researchers at the University of Sussex. We're going to look at these two experiments to start with. The first experiment here from Professor Mondada was using a Kepler robot. This was back in the early 1990s. This series of robots are still being made. I put a link down there to the latest version, Kepler 4. You can go and have a look. Relatively inexpensive, useful for experimentation, simple robotics experiments and education and so forth. You've probably heard of the Kepler's much more famous cousin, the Roomba. As you can see, the Roomba and the Kepler are kind of similar. Both have two wheels. One of the nice things about the Kepler is it's very small. It's about the size of a hockey puck. So you can put it on a table and carry out experiments on a tabletop. The other nice thing about the Kepler is it has this modular architecture where you can snap on extension modules on top of the base chassis of the robot. Here's a little picture of a simple gripper. This gripper can rotate down, close the gripper and grab, for example, a sugar cube, lift it up, and then with the wheels transport that object somewhere else. Later in the course, we'll see an experiment that uses this simple gripper system. You can, for example, add a simple vision system. Again, this was somewhat primitive, but state-of-the-art in the early 1990s. In this case, we have a linear vision module sitting on top of the robot, as you can see in the cartoon here. This linear visual module has a range of vision of about 36 degrees in front of it, and it gets back from its various photoreceptors different light intensities. More light intensity obviously means that in that direction there's no obstruction, but a dark image represents that that photoreceptor is close to a dark object. We're assuming it's in the presence of dark obstacles here. So again, not very sophisticated vision, but simple vision. In the experiment we're going to look at here, this is the very first experiment done in evolutionary robotics. They built the Kepler robot, and then as you see in the top right here, they placed it on a tabletop and they wired up a tether to the ceiling and then on to the computer. Computation was pretty limited at that point. You definitely could not do much computation on board the robot itself. So all of the evolutionary computation was done on board the computer, as well as the neural network. So the brain of the robot is inside the computer. At every time instant, when values arrived at the motor layer of the neural network, those motor commands were sent up and through the tether down to the robot, which were received by the actual motors in the robot. The robot did its thing, it moved, and the moment it moved, those changes in sensor values were sent back up the tether to the computer, and those values were input to the neural network running on board the computer, and we closed the embodied loop going back and forth between the computer and the Kepler itself. Most robotics experiments today, obviously the neural network is running on board the robot. Okay. They also had this little laser emitting device, which you can see up here in the corner, that emitted a laser and swept through this space that the robot lived inside, and there was a little additional sensor sitting on top of the robot that could pick up information about the laser, and there was a very simple calculation that the robot did on board, sent that calculation back, and using that calculation, the computer could figure out the X and Y position of the robot on the tabletop, as well as alpha, the heading of the robot. So the computer knows where the robot is and where it's headed. The robot does not have that information. The robot has, in this experiment, these simple proximity sensors. So again, not that different from a Bratenberg vehicle. We have 6 of these proximity sensors arrayed along the front of the robot, and a 7th and 8th proximity sensor on the back of the robot. These proximity sensors would emit values between 0 and 1. 0 means there's no obstacle within 5 centimeters of me. 1 means I'm touching an object, and a value between there means there's an obstacle some distance away. The further the object is away, the lower the value of the proximity sensor. We've got 8 proximity sensors. They're feeding into 2 motor neurons, which are sitting in the center of the robot here. It's just drawn a little bit differently. 8 sensor neurons, 2 motor neurons, and they send their 2 values to the motors controlling the left and the right wheel. In this cartoon, it's drawing the neural network right on top of the robot, but remember the neural network is being run on the off-board computer. So far, so good? Okay. The values that are arriving at the motor neuron, the 2 motor neurons, are squashed by an activation function to lie between +5 and -5. A value of +5 means the wheel should turn as quickly as possible. -5 means they should turn backwards as quickly as possible. And if the motor neuron has a value of 0, that means hold the wheel still. So we've just looked at 2 different motor layers in 2 different robots, a wheeled robot and a legged robot, which is a reminder that the values that are arriving at the motor neuron, from the neural network's point of view, the neural network's done. It doesn't know how those numbers are evaluated. It depends on which robot we drop them into. If we drop this neural network into a robot that has a rotational hinge joint, we treat those values as desired angles. If we drop this neural network into a wheeled robot, we treat those values as desired rotations per minute, or speed of the rotation of the wheel. Right? Okay, so let's just pop back here for a second. So there's our setup. We're going to evolve neural networks for this little tabletop robot. The computer knows the X, Y, and heading of the robot. And the robot, at any instant of time, has 8 numbers, which are the proximity sensors, and it can change its behavior based on those proximity values. What kinds of behaviors might we be able to evolve for this admittedly simple robot? Yep.
Turning in response to a certain signal.
Turning in response to a certain signal, yes, okay. What kinds of signals? Could the robot evolve to stay on the table, given what I've just told you about its sensor and motor complement?
I mean, as long as it's just an ordinary table, then no, because it'll never see where the edge is.
Exactly. We can see where the edge is. The robot can't. So in all the experiments we're going to look at in this course, you need to put yourself in the shoes of the robot, right? You can't see in 3D and color and hear and sense and so on. You're the robot. All you get are these 8 values at one time instant to the next. So you cannot see the edge of the table, which means you can't evolve to stay on the table. You may be able to see and turn away from obstacles that are placed on the table. That's possible, right? Okay, let's look at what they actually did. So they built this relatively simple race course or maze on the top of a table that you see here. And they're going to try and evolve it using a fitness function, which we're going to build up in a moment, where the fitness function is that they want the robot to circle through the maze as fast as possible, do as many laps around the circuit as possible, and don't touch the walls. Pretty simple. Okay, let's assume we're going to build up this fitness function here, and we want this fitness function, this value, to range between 0 and 1. So whenever we drop a neural network inside the physical robot, it's going to do its thing inside the race course, and we're going to then assign a value, the fitness, to that neural network. 0 means the robot did the worst possible thing, which is probably sit there and do nothing, or turn and smash into the closest wall. And 1 is going to be the highest possible value. It's going to be we're going to assign a value of 1 to any neural network that gets the robot to race around the maze as quickly as possible. Let's build up this fitness function using the following 10 variables. Let's assume that we can pull off the robot at every instant in time as it's doing its thing in the maze here. We can pull off the speed of the left-right wheel, which you'll remember ranges between minus 0.5 and plus 0.5, and the 8 values of the proximity sensors, the 6 on the front and the 2 on the back, and those range between 0 and 1. How might you go about building up a function of these variables that will give us a 0 for worst behavior and 1 for best behavior?
Does it matter? Well, it seems like it would matter on which way the robot is circling the maze.
Does it matter? All we said is race around the maze as quickly as possible. We did not say race forward around the maze or backward. Let's assume it doesn't matter.
Does it have sensors on the back of it?
It does.
Okay.
6 on the front and 2 on the back.
It would seem that they will probably move forward then because it has more sensors there.
It would want to move forward because it has more sensors on it. Does this robot want? Does it love? Does it hate? Bradenberg tells us no. But maybe if we evolve it, we might get forward locomotion, forward movement more often than we get backward movement. Maybe because there's more sensors on the front. It seems obvious, right? We have more sensors on our front, so we tend to move in the direction in which our sensors are facing. It's obvious. That's the way to do it, right? Except, remember the warning? What's our warning as we move forward through this course? Thinking about thinking is misleading, right? We have forward-facing sensors, so obviously moving forward in the direction of which you have most sensors makes sense. Is that really true for this robot? Could it race backwards through the maze just as well using its 2 backward sensors? Hard to tell, actually, right? So let's find out. Let's evolve some behaviors for this robot, and let's, for fun, not build into the fitness function a commandment saying thou must move forward. Forward or back doesn't matter as long as you move quickly through around the maze without touching the walls. How do we do that? What are some of the components of this fitness function that we're going to have in place?
Vehicle speed.
Sorry?
Vehicle speed.
Vehicle speed, okay, but we have speed of the left and the right wheel. We don't actually have vehicle speed. You can maybe compute it using VL and VR. How might we do that? How would you compute the fact that the robot is actually moving forward or back?
You do it like with vectors.
Okay.
Vector for the right wheel, the left wheel, the length of the vectors, how fast that wheel is moving, and we can know some of them.
Possibly. So we could create a vector for VL. We could look at VL at T0, T1, T2, and T3. Is that what you had in mind?
Yeah.
Okay, so we could do that. We could take the vector, all the values of VL over time. Let's assume we're going to evaluate the robot for 20 seconds. And however many time instants we get, we have a vector for VL and a vector for VR. What are we going to do with those 2 vectors then? Let's actually assume that VL and VR are vectors.
So we may try to maximize the velocity while keeping the proximity sensors at 5, and that might.
Exactly. We're going to try and maximize VL and VR somehow, right? While at the same time trying to keep the I values at intermediate ranges. So there's 2 things we have to do here. So we can think about maybe 2 two parts to this equation, two terms, one which rewards for speed of movement and the other which rewards for obstacle avoidance. Let's focus on the speed one. We're getting close, but we need to actually describe this as a function of VL and VR.
If VL and VR have the same sign, then it's moving. Like
If they have the same sign, then it's moving. What if they have different signs? What does that mean? It's turning, right? Okay, so let's have a look at what they actually did. We're going to look at actually three terms. Let's look at uppercase V for the moment. They simplified things by just taking the absolute value. If you want, you can think of this as absolute values of the elements in the VL vector. Doesn't really matter. We're going to take the absolute values and then sum them together. And if we do that, again, we know VL and VR range between minus 0.5 and plus 0.5. So we guarantee that uppercase V ranges between 0 and 1. But uppercase V alone does not guarantee forward movement or backward movement. Why not?
Might just start rotating.
Absolutely, right? We could have VL equals minus 0.5 and VR equals plus 0.5. Take the absolute values and sum them, we get 1, and we get a robot that's rotating in place clockwise or counterclockwise. So V alone is not going to do it. So we're going to multiply that by delta V, and as the name of this term implies, this value is going to be 1. This value is going to be 1. Delta V is going to be 0 when it's traveling forward or back, and 1 if it's turning in place. But we want to try and maximize this function. So we're going to take 1 minus delta V, and then they built in one additional element here, which is the square root of delta V. So if we have the square root function, this means that when x equals 0, and we'll assume that x is delta V here. So when delta V is 0, that's fine. When delta V, or the difference between the two values of the motor, starts to diverge, so we get non-zero values of delta V, the square root of delta V goes up very quickly. So we're penalizing very harshly any difference between those two values. Okay. So overall, delta V is, uppercase V is saying, go fast or turn the wheels fast. Delta V is saying, try and keep the velocities of the wheels as close as possible. Multiplying V and the delta V term together doesn't say anything yet about forward and backward, right? So far, so good? Okay. Now we're going to take 1 minus I, and 1 minus I because we're going to define this term I, which is just over all the 8 input sensors, what is the maximal firing one? The one that fires most strongly. And remember that the proximity sensors fires most strongly when it's very close to an object. The more that happens, the more we're going to penalize you, 1 minus that value. So we're rewarding for uppercase V, we're penalizing for delta V, and we're penalizing for I here. So far, so good. You're going to see a lot of fitness functions in this course, and a lot of them sort of have this form where some of the terms are reward terms, like V, and some of them are punishment terms, like 1 minus. We're combining these things. Do this while at the same time don't do that. Okay. What do we get? Here's what happens over evolutionary time. This is known as a fitness curve plot, because we're plotting on the horizontal axis here evolutionary time. We have a population of these neural networks. We're evaluating the fitness of all of them, throwing away the ones with low fitness, making randomly modified copies of the ones with higher fitness, and repeat. And if you do that, obviously the mean fitness of the population of a whole is gradually going up, which is the lower curve that you see there. And then the upper curve is the fitness value of the best neural network in the population at that time. The researchers carried out a total of 100 generations here, evaluating each neural network in the population. For one generation took 40 minutes. This experiment took 66 hours to carry out. It's quite a bit of time to do this relatively simple experiment. Why did they bother with the physical robot? Why didn't they just do this in a physics engine?
They did not want to deal with the gap between.
They may not have wanted to deal with the reality gap problem, maybe, although that problem was not known at this time. This experiment was carried out in 1994.
They just not have the computational power.
They didn't have the computational power, and there were no physics engines. The first commercially available physics engine was around 2000, introduced by the video game industry. It's ubiquitous now. They used a physical robot because there was no alternative at the time. A very painstaking, effortful experiment, but definitely shows that a physical robot, without pre-programming it, you can autonomously design, using evolution, an autonomous machine, a machine that autonomously decides how to move and how to turn on this race course.
This fitness function seems like it doesn't have a way to guarantee that it's going to go around the track. It could just go forward and back.
It could do that, right? Why doesn't it travel and then turn 180 and head in the other direction? Why does the trajectory that you see at the bottom, that's the trajectory of the most fit robot in the population, why did that one win out over ones which probably did move forward, turn 180, and head back in the other direction?
Well, it has to reduce its speed to turn around, or if it's continuously going in the loop, it can maintain.
It's hard to see from these images, but it probably would have to slow down a little bit and turn on the spot. And for those time instants at which it's going slow, its uppercase V is going down, and it's turning on the spot. So delta V is also going way up, for which it's being punished. So that combination was probably enough to weed those solutions out.
What if it doesn't turn around and just goes straight back and forth?
So maybe it doesn't have to turn around, but it probably, again, has to slow down, which brings down uppercase V. Maybe it could figure out a way to not bring down delta V by not turning. But again, you could imagine they probably set things up in just such a way that this did not happen. Those solutions probably existed, but in this case, they got what they wanted. In this little picture here, we're showing at the center of each of these line segments the position of the robot at that time, and the orientation of the line represents the heading of the robot. That line threads through the left and the right, the center of the left and the right wheel. Is it going forward or back? Who knows, right? Okay. Let's break down this fitness curve a little bit more. As we just saw, the fitness function is made up of these three components, which are plotted here. I apologize for the quality of this image. You can see uppercase V is the solid line, and that value climbs during about the first half of this evolutionary process, which tells us, and sorry, this is for the best robot in the population at each generation. That tells us that over evolutionary time, neural networks are evolving that get the robot to to spin its wheels faster and faster. So uppercase V is going up. If we look at the dotted line, that's 1 minus delta V. What's going on with 1 minus delta V over the evolutionary process here?
Becoming less volatile.
It's becoming less volatile. It's sort of evening things out and traveling a little bit straighter. But again, kind of hard to see. And 1 minus I, which is the dashed line, starts a little bit high and then comes down a little bit. Remember that the fitness function is actually trying to maximize all three of these terms. We're trying to minimize I, but maximize 1 minus I. We're trying to maximize, we're trying to minimize delta V, but maximize 1 minus the square root of V. So really, in theory, we should see all three of these components increasing at the same time. That's not what we see. We see one increasing, the others coming down a little bit, and then staying more or less steady. So this is a reminder to us that by posing this fitness function to the evolutionary process, we're challenging evolution to try and balance these terms. It's always a trade-off. If you start moving through this maze and you want to avoid obstacles, by necessity you're going to have to turn, which means you take a hit on the delta V term. If you try and go straight, you're eventually going to hit something. So you're going to take a hit on the 1 minus I term. There's no perfect solution here. Evolution is not an optimizer, it's a satisficer. Evolution, both biological and artificial, tries to do the best it can with the materials at hand, and usually it tries to strike a balance as best as it can. It doesn't always find an optimal solution, but often an optimal solution is not what we're looking for. We're looking for a solution that's good enough, whatever that means. Question?
Was the fitness function also like summed over the time of
I think so. I think if you go back and read the original research paper, it's a little bit vague, but I think it was summed over. I think these were all vectors, more or less. It was calculating this at each time step and then averaging that over the lifetime of the robot.
Would the best robot after all the generations work in a different phase?
Good question. Remember we talked about overfitting when we talked about neural networks, which is a tendency for all machine learning algorithms, given the opportunity to do so, to cheat and memorize the situation, which in this case would be memorizing the shape of the maze. Very difficult to tell what it would do. Right? What we could do is take the best evolved neural network, pick up the robot, and put it at various positions in the maze. So from our point of view, it's still the same maze, but from the robot's point of view, it may suddenly be in different parts of the maze that it had never seen before, and we could see how it does. But there is no formal guarantee we can make that it will or won't generalize to those novel situations.
Did they randomize the orientation when they put it starting?
Again, the research paper is a little vague on that. You can go back and read it. I don't think they did. I think they tried to set it at more or less the same set of initial conditions. So my guess is it's probably pretty fragile. Okay. Okay, this is another plot of exactly the same data, which we're now plotting in 3 dimensions. Let's look at the cube on the left. We have a 3-dimensional plot here where the 3 dimensions of this plot correspond to the 3 fitness components. Each dot in this cube corresponds to one neural network, and that neural network was the best neural network in the population at that time. And they trace the trajectory of where these dots are moving to, which if you kind of squint, you can see that these dots are moving up in the cube somewhat, which means they're somewhat increasing 1 minus I, and they should also be moving towards the right side of the cube, which means greater uppercase V. A little hard to see here. They then did the same thing for just one controller. So here's the robot starting in the maze where all the values, the value of V and delta V are 0. It's starting with no forward velocity and no difference between delta V. And then gradually, as the robot starts moving, these 3 fitness components are changing while the robot is behaving. And we can see sort of visually how the robot is striking a balance between these different fitness components. It's just a different way of visualizing the evolutionary process. This is very different from the fitness landscape, where every point in the surface of a fitness landscape was a different neural network, and the height was fitness. Just a different way of plotting the data. Okay. In trying to answer the question about how well does this robot visualize, they did pick it up and put it back and take the best evolved neural network and place it in different positions in the maze. For example, they took the robot and placed it facing into this corner down here, and the evolved neural network drove towards the corner and then turned to its left by 180 degrees and took off down the lower part of the race course. They then took their neural network here and they manually set the synaptic weights. So they set aside the evolved neural network, manually set the synaptic weights, which, as we've seen over the last couple of weeks, is a very difficult thing for a human designer to do. In this case, you can just do it if you think carefully about the robot situation. Here's a visualization of the actual settings of the weights, which is based on a Bratenberg vehicle. If you look carefully and you look at the arrows of these incoming synapses, which are going from the sensor neurons to the motor neurons. Some of them are arrows, and some of them are this sort of inverse arrow here. The normal arrows represent excitatory connections, and remember that excitatory synapses are positive values, and inhibitory connections are negative values. If the proximity sensors are firing, and that value is passing along an inhibitory synapse, for example, from this proximity sensor on the right to the left motor neuron, what is that doing to the wheel? We've got an obstacle sitting right about here, which is causing that right proximity sensor to fire more strongly and more strongly inhibit this left-hand motor neuron. That should sound very familiar to you.
Take a right turn.
Take not a right turn.
The right sensor is firing strongly.
Strongly. The right sensor is firing strongly, so it's strongly inhibiting the left motor.
The left motor stops.
The left motor is going to more likely turn back, because remember, negative means rotating backwards. Depends on what, obviously, the other incoming synapses are trying to get the motor neuron to do. But if we just focus on that one sensor-motor pair, more stimulation on one side causes more inhibition on the contralateral or other side, which means the wheel either slows down or starts to turn in the other direction. And assuming the right-hand wheel is turning forward, it will turn away from the obstacle. This is the coward, right? Bradenburg vehicle 2A. It's just got a few more sensors. So if you look carefully, you'll see that all the contralateral connections here going across the body are inhibitory, and all the ipsilateral connections, same side connections, left sensor to left motor or right sensor to right motor, those are all excitatory. Why? Why are the ipsilateral connections excitatory? So let's go back to our example here. We have an obstacle sitting right here, which means our right proximity sensor is firing strongly. And if we now follow one of the excitatory connections down to the right motor,
and it spins the motor on the same side so the robot ends up turning away.
exactly, right? So stimulation on the right passes through excitatory ipsilateral connections, causing the same side motor to spin faster forward. And the same sensor value is traveling contralaterally and inhibitory down to the opposite side motor, which is trying to get that motor to stop or even turn in the other direction, so it turns away from the obstacle.
Did they find that the weights were not symmetric based on the direction that the robot traveled?
Yes, you've stolen my thunder here. So you can see in the Bradenburg vehicle here, the width of the line is the magnitude of the value of the synapse, right? Some of these synapses are positive or negative. Fatter lines mean further away from zero. This one that they made by hand is perfectly symmetrical, which makes sense, right? You look at lots of animals, we are bilaterally symmetric. Say our left side of our bodies look the same as our right side of their bodies, so it's obvious what we should do in this case, right? So once we've figured out this ipsa, contra, excitatory, inhibitory pattern, we set the actual magnitudes to be bilaterally symmetric. Obviously that's going to work, doesn't work. If you have a robot that happens to start to head into, for example, the corner that you see here, there's this same average stimulation of the sensors on the left and the right side, which means the wheels are trying to do more or less the same thing, and it's gradually shifting back and forth and wedging itself further and further into the corner and cannot get out. This one, which they pointed directly into the corner, always turns to the left, because if you crack that open and look at what's inside, the magnitudes of these synaptic weights are not bilaterally symmetric. Close, but a little off. for a good reason, right? In retrospect, it makes sense, but going into this experiment, we would have said, we know what the solution is, bilateral symmetry.
Does that cause it to always go around the track in one direction?
Yep, absolutely.
Did they try going in and flipping the evolved weights and then seeing if it performed in the opposite direction?
Good question. I don't know if they tried that. They didn't report it in the paper. Be a good thing to try. Okay, one more observation to make about the one evolved neural network here is that the top speed of the wheels, if the wheels were spinning at plus 0.5, as fast as they could go, if both of them were spinning forward, the robot would travel 80 millimeters per second, super fast. But the evolved neural network never passed 48 millimeters per second. Now that kind of makes sense because obviously it's got to slow down a little bit to get around the turns, but when it's in a straightaway, it never accelerated to 80 millimeters per second. They did this a couple times and they got different solutions and it always seemed to top out at 48 millimeters per second. Why? We may not know why it's 48 rather than 47 or 49, but why less than 80?
Was it processing time for the sensors to the motors? Like if it went in faster, it would miss signals?
Absolutely. So the sensors, the proximity sensors here, they report their values, again, at certain discrete time steps, not unlike our physics engine. I don't know what those discrete time steps were, but basically the robot is seeing its world in a series of discrete frames. And whatever the frequency of those discrete frames were, the top safe speed, 48 millimeters per second, right? So we have a solution which is, first of all, non-obvious. It's not bilaterally symmetric. And it's also autonomously, evolution figured out for us what the top safe speed is of this robot. We didn't have to figure it out by hand. Good thing we didn't try and build in a fitness function that said travel at 80 millimeters per second, because unbeknownst to us, that's unsafe given the physical limitations of this particular machine.
If we were to stretch the map in one direction and have like a super long straightaway, do you think it would reach the top speed of 80?
Maybe, possibly. You can rebuild this in PyroSim if you're interested. PyroSim allows wheels as well as legs. You can place external objects and build up the raceway. Again, if you're thinking about a final project idea, this might be something to try out, and you could actually tackle some of these good questions. Okay, let's move on now. We're going to jump across the English Channel. We were just looking at one of the initial experiments. At about exactly the same time, another evolutionary robotics experiment was being carried out at the University of Sussex in the UK. If you're interested in the history of science, this tends to happen. There tends to be particular ideas that are in the air, and suddenly there are multiple publications of this approach or this method or this phenomenon at about the same time. Kind of interesting if you're interested in the history of science. Here's an example of that. The researchers at the University of Sussex built this very interesting looking robot, which not surprisingly they named the gantry robot. It's a little bit of a Rube Goldberg contraption here. We have a table in which they've removed the upper surface of the table. They then placed this wheeled gantry on top. This one here, which they called the X-Trolley. The X-Trolley, as the name implies, can roll forward and backward along the X-axis of the table. On top of the X-Trolley is a smaller Y-Trolley, which is rolling back and forth on the Y dimension on the back of the X-Trolley. Okay? Then they threaded it down, again with the tether. So we have the same situation here. We're sending sensor data back along the tether to the computer. The computer pushes those sensor values through a neural network and sends the motor neurons back through to the robot. Through the smaller trolley on a tether, they hung an inverse or upside down periscope. Remember periscopes from submarines that do this? In this case, it's upside down. We have a camera which is sitting right here, and that camera is pointing straight down. That camera is looking down at a small dental mirror, which you can see right there. And that dental mirror is angled at 45 degrees. So the camera, the photons coming in from the horizontal direction are hitting the 45-degree angled dental mirror and up into the lens of the downward pointing camera. So far, so good. We have 3 motors on this robot. The first motor controls the movement of the X trolley, back and forth, positive and negative X. Second motor controls the Y trolley, plus and minus Y. And the third motor down here rotates the dental mirror, like the periscope, right? So it can look around the undersurface of the table. So they can now, like the other experiment, they can put obstacles and other things on the floor underneath the table. And the robot itself is really this thing that's moving horizontally, X and Y, about the scene on the floor underneath the table. This larger disc that you see here, this is a bump sensor. So if that larger disc comes into contact with any objects, that little disc is deflected by a small angle, that's registered, and that's one of the sensors. So we're going to have a bump sensor, which we'll talk about in a moment. Also the visual sensor. So we have this simple camera that's getting a simple image of the scene underneath the table, and these 3 motors. Why the heck would these researchers make such a crazy contraption? There is an advantage of the gantry robot over doing something with a wheeled robot on a table. What is it?
Not in this form, but it looks kind of like a 3D printer in that it could eventually go in the Z direction also.
Possibly. They could have maybe a third trolley. They could maybe find a way to get the periscope to move up and down, and we could control 3 dimensions of motion under the table.
It's a simplified control system. I mean, you have a motor that controls X, a motor that controls Y. You don't have to do rotations.
Maybe. Same thing here. We have 2 motors, one that controls the left wheel and the right wheel. What's that? It won't fall. That's one advantage, absolutely. What else? Also, this one wouldn't fall because it's inside the raceway.
Fewer sensors.
Fewer sensors. It has about the same. We haven't talked about the visual sensor yet. We'll talk about that in a moment. Why go to all this effort?
I mean, depending on what they're using to control, it can be a lot more precise.
It can be a lot more precise. Precision definitely is part of the answer here. Remember that this is going to be an evolutionary robotics experiment. So they're going to try out dozens of neural networks, one after the other, on this robot. Once they've evaluated dozens of neural networks, they've finished generation 0. They're going to delete some of those neural networks and make randomly modified copies of the ones that survive. Evaluate all of those, rinse and repeat. The reset, exactly. Our poor researchers over in Switzerland, they had to take the hockey puck Kepler robot and put it back at the starting position every time, hundreds, possibly thousands of times over those 66 hours or however much it was. So the gantry robot, it's more complex, but we justify the cost of that added complexity because we've automated more of the evolutionary process. We can reset the initial position of the gantry robot. That's why. Okay, so let's talk more about the sensors and motors. As I just mentioned, it has this bump disc underneath, and depending where on the edge of this bump surface it's hit, it can detect that, and we're going to discretize that down into 4 virtual sensors. We're going to talk in this course about virtual sensors, not virtual in the sense that they exist in a physics engine, but virtual in the sense that we have one physical sensor, which is detecting the deflection of the bump disk, and depending on the direction of that deflection, we're going to use 4 binary virtual sensors. The virtual sensor is going to light up with a 1 if it says I got bumped in my quadrant. The other bump sensor is going to light up if it says I got bumped in my quadrant, and so on. So we have 4 touch sensors. Where on the disk did the robot got touched? And then we're going to create from our raw camera image, we're going to distill this down into just 3 numbers. And we're going to do it in the following way. The evolutionary algorithm here is going to not just optimize the synaptic weights of the neural network, it is also going to output 9 additional numbers, 3 triplets, and those 3 triplets correspond to the 3 circles that you see here. So let's start with the raw CCD, or the camera image here, which gives us north, west, east, and south. They then do a little bit of image processing to turn this into a 360-degree view. Remember that the dental mirror is rotating, so it sees 360 all the way around it. When it does one of those sweeps, we're going to compress that down into polar coordinates. So we've got a sort of warped image of everything around the robot 360 degrees. And then on top of those polar coordinates, the evolutionary algorithm is going to drop 3 circles. It's going to output the X and Y position of each of these 3 circles, and finally the radii of each of these 3 circles. So we have X, Y, and R for 3 circles, which give us those additional 9 numbers. So in essence, each genotype, which remember is the blueprint for how to create the phenotype, that genotype has 2 sets of numbers, the synaptic weights and the 9 numbers that are dropping those 3 circles onto the raw visual input. Why are they dropping these circles? What they're doing is allowing evolution to evolve a visual sensor where the neural network is going to focus where it looks at the scene. So in this little cartoon example here, evolution has produced these 3 circles at these 3 positions and with these 3 radii. At each time step at which the robot moves, we're going to take all of the pixels that lie inside of each of these 3 circles, throw away the RGB values, collapse them to grayscale values, and then just take the average grayscale value inside each of these 3 circles, represented by the grayscale that you see here. And those 3 numbers, in addition to the 4 binary touch sensors, become the 7 sensor neurons that feed into the neural network. Remember, this experiment was done in the early 1990s. There was no good way to take raw video footage and input it to a neural network. Still a bit of a challenge today. So they said, evolution, you figure out how to pull out a subset of information from this raw visual field. These are known as receptor fields. Mammals also have this in our eyes, so you don't feel it, but you have a receptive field right at the center of your field of vision. When you're looking at my face or the slide, all of that is in focus because that's falling at the center of your visual field, which is where there's a receptive field. Everything else in your field of view is very foggy and low definition, unless obviously you saccade or move your eyes and look there. We have receptive fields right at the center of the back of our eyes. In this case, our robots may have up to 3 of these receptive fields. So far, so good? Okay, so we have these 7 sensors, and we're going to ignore the rotation of the camera. Let's just assume that the camera rotates at a constant velocity. So we'll only have 2 motor outputs, movement left and right, or plus x minus x, and plus y minus y. So the commands from the neural network are going to move the 2 trolleys, and while the 2 trolleys are moving, the dental mirror is spinning around underneath, producing this polar coordinate raw visual feed for us. Okay, we'll finish today by talking about the fitness function. In this case, they used an incremental evolutionary approach. We're going to see this many times throughout the course. They're going to try and evolve a relatively difficult task, more difficult than racing through a racetrack. So they're going to create 3 different fitness functions that you see here, 1, 2, and 3. And these 3 fitness functions are going to select for incrementally more complex behavior. The first behavior is they're going to place a black piece of Bristol board on the back vertical surface of the table behind it, no obstacles on the ground, and they're going to reset the gantry robot to these 2 initial positions. Start at this initial position, the robot moves. When it finishes moving, they command the gantry robot to move to this position, then release it, and the neural network controls the gantry for a second time. So each neural network has 2 attempts to move. In this case, the fitness function is very simple, which is approach the back black wall underneath the table. What's the fitness function here? we have, to build up this fitness function, we have the values coming from these 3 receptive fields, which remember are grayscale. And we can also assume we have the values of the position of the gantry, the 2 gantries. So the robot knows its position, and it has the average grayscale inside of these 3 receptive fields. What kind of fitness function could we build up from that? Idea?
It's distance from the back wall.
Pretty straightforward, right? There's different ways we could do this. Let's assume that the back wall is at maximum y. So we're going to try and just maximize the y coordinate of the y gantry. Pretty straightforward. Sorry, I misspoke. There aren't actually 2 trials per neural network. There are 4 trials. I'm just showing 2 in this cartoon here for clarity's sake. Okay, we'll talk about fitness function number 2 and number 3 on Thursday. You have a quiz due tonight. Undergraduates, you're tackling assignment, I've forgotten. Assignment 4. Grad students, you're on to 7 and 8, and I will see you all on Thursday. Thank you.